And also, I must tell you that whatever I have done, first 2, 3 lectures of this series, those things, most of things I have done in my PhD time actually, not even in MSc. Because in MSc also I didn't do that seriously. In MSc level, I didn't know what actually reciprocal lattice means. So when I went for PhD, I was asked to give a seminar, first seminar during my coursework on reciprocal lattice. So then I kept on searching what is a reciprocal lattice, how will I define? Only I know that B1, B2, B3 in terms of A1, A2, A3. Other than that, I have no idea. And I searched in the library a lot. That now at least you can search everything in mobile. That time you have to go to the library and take out all old books. I spent around 2 months searching for reciprocal lattice. Then finally I came to some understanding and gave some seminar that was okay. So that's why I was more interested in that. Okay. But without mathematics, those things cannot be understood. But now, when we go for X-ray diffraction, what we need is basically this is lecture 5, X-ray diffraction. Okay, I will not put any subsections in that, it's just X-ray diffraction. So when you want to know diffraction, first you have to understand what is the diffraction actually. Okay. So all of you have studied already Young's double slit experiment. Young's double slit. Everybody has studied, probably in +2 and degree also they may be studying. Young's double slit. Is it interference experiment or a diffraction experiment? People know that it's actually interference experiment, right? Young's double slit you study for interference, not for diffraction. So, how do you distinguish between interference and diffraction? Sometimes it's confusing actually, because usually we know that when the object or slit sizes are very small, of order of wavelength, then diffraction effects come into picture, right? Diffraction takes place when the size of the object is of the order of the wavelength you are using. If the size of the object is very big, very large compared to wavelength, diffraction effects are not seen actually. So when the slit size is of the order of wavelength, then you start getting diffraction effects. But in Young's double slit experiment, where both the slits are extremely narrow, even you go, the slit size even smaller than wavelength actually. At that small slit sizes, why don't you call it Young's double slit diffraction experiment? But that's not diffraction experiment, it's only interference experiment. You only study the interference because you have two slits separated by a small distance, because the waves are coming from two different slits. That superposition of the waves, you call it interference. But if you see Young's double slit experiment, if you close one of the slits, the double slit experiment, if you close one of the slits and look at the screen, what happens? You see that whole screen is bright actually. The brightness will be almost uniformly distributed on the screen. You close either of the slits, it doesn't matter. So if you have very, very minute slit size, how light is going all over the screen? Is there a diffraction or no? Yes, actually it is because of diffraction, it gets distributed on the other side. On one side it's going as a parallel beam, other side it diverges throughout the screen. So diffraction occurs for the light which is entering through the slits. But the problem is, are you observing the diffraction effect? Diffraction fringes? No, because what we do, if you take a slit size, some nominal size let's say, and pass current through, let's take 1 mm for example, slit size, and pass some light through that, parallel light. You will see on the screen 1 mm sized brightness. Slit image you see basically, that's a 1 mm size. Then you slowly reduce the slit size. When you go to micron size, you still see single image, that slit only will be parallel, light is going on. But as you reduce more and more, when you go, the slit size goes down to let's say several thousand angstrom, because your visible light wavelength is 4,000 to 7,000 angstrom. Let's say you go down to suppose 15,000 angstrom. Then you see slowly you are reducing the slit size, but the image on the screen will be widening actually. And if you further reduce, it will widen up further. If you keep on reducing the slit size, what will happen is that slit size is extremely small, but brightness is there throughout the screen actually. That intensity is distributed uniformly throughout the screen. That means it is because of diffraction. But diffraction fringes, if you want to observe on the screen, slit size should not be very, very small. You keep it around the wavelength or a little larger than wavelength. You will see the fringes on the wavelength on the screen. It is slit size is very small. You will not see because they will go out of the screen. The diffraction effect is there, but that cannot be observed on the screen. Because you want to make interference experiment. That is, interference is occurring between the two sources which are separated by a small distance in Young's double slit. You want to remove these diffraction fringes from the screen. Otherwise, each slit should give you diffraction fringes. But the slit size is extremely small, you will not see that. Okay. So each slit is producing uniform intensity separately. But when you open both of them, these two slits are giving rise to waves on the screen which are interfering constructively and destructively depending on the position. That gives rise to maybe center bright fringe, alternately dark and bright above and below. Okay. So what this means, if you want to observe interference fringes, you should remove diffraction effect from the screen by making its slit size extremely small. That's what M did actually. If you increase the slit size slowly, both the slits will start increasing the slit size a little bit. What will happen? You will have interference effects. This diffraction fringes also overlap on that. Then it's difficult for you to distinguish which is due to diffraction, which is due to interference. That's why you need extremely small slit sizes. But we have studied already single slit diffraction. That is there. But single slit diffraction, you see, we never use slit size which is extremely small. No. It is of the order of wavelength or little more than wavelength you must have. You cannot use it slit size extremely small actually. Okay. Now, when we are talking about light diffraction, we are talking about the slit of the size of order of wavelength of the light. That is 4000 to 7000 angstrom. But if you look at X-rays, X-ray wavelength is of 0.01 nanometer to 10 nanometer overall range. But X-rays used for X-ray diffraction experiment are around 1.5 nanometer, sorry, 1.5 angstrom. That is 0.1 nanometer, 0.15 nanometer. When you have such a short wavelength, you also need to have a slit which is of that order, right? Otherwise, you cannot see diffraction. So, but in solids or crystals, the atoms are separated by a few angstrom distance. The separation between the atoms is very, very small, of the order of X-ray wavelength. That is why visible light cannot produce diffraction effects for the crystal side. You take a crystal and shine visible light and see. You will see that light is just like reflected because wavelength is so large, because you are talking about 5000 angstrom wavelength and your slit sizes are maybe 2 angstrom, 3 angstrom. So the wavelength is much, much larger. When you have a large wavelength, that wavelength will see, that light will see the solid as if it is continuous, because it, within one wavelength, it is seeing, let's say, 7000 atoms or 5000 atoms in one wavelength. But that wave feels as if your medium is continuous actually. So that's why visible light cannot distinguish between the atomic separation actually. It takes as if it's a continuous medium. That's why crystal structures cannot be obtained by other radiations like visible or ultraviolet radiations. They have very, very large wavelength. But what about gamma rays or something with a very short wavelengths? So these are different effects are there, because if you take how electromagnetic wave interacts with matter, you have to look at that actually. If the energy is very high, you will get into this Compton scattering, pair production, etc. They are more prominent compared to X-ray diffraction actually. That's why for moderate energies, if you take for X-ray diffraction, usually maybe 8000 eV or 8 keV, around that energy they take. If you keep on increasing energy, you will have less probability for diffraction, but other phenomena will take place, Compton scattering or pair production. If you go very high gamma ray region, then you pair production will be possible. Pair production takes place because of the electromagnetic photon interacting with nucleus actually. Okay. So that's for very high energies. For moderate energies, you can have X-ray diffraction. So because this wavelength of the X-ray is almost the order of the atomic separation actually. That's how this works. Okay. So now if you actually look at why X-ray gets diffracted by the lattice or crystal, you have to understand. That means when X-ray falls on an atom, what happens? You know how what happens when X-ray falls on an atom. So what is an X-ray basically? X-ray is nothing but electromagnetic wave that everybody knows. Okay. So it has a frequency of the order of 10 to the power of 16 to 10 to the power of 19 hertz actually. Very high frequency electromagnetic radiation. So frequency starts at 10 power 16 to 10 power 19 it goes. Okay. So when you have such high frequency electromagnetic wave, but electromagnetic wave is not nothing but electric and magnetic fields at perpendicular directions, right? And it's oscillating electric field and oscillating magnetic field also. But what is the frequency of oscillation of the electric field? That is the same frequency. X-ray frequency is that only. We talk about X-ray frequency 10 to the power of 16, I am saying. That means electric field is oscillating with a frequency of 10 to the power of 16. Very fast varying, fluctuating electric field. Similarly, magnetic field also varies with the same frequency, vibrates with the same frequency. When you have such fast vibrating fields, such a X-ray falls on the atom, let's say. Now let's take a single atom. It falls on the atom. What will happen? Atom contains electrons, right? Electrons are negatively charged. So when X-ray goes and interacts with the atom, electrons start vibrating because electric field gives a force on the electron, oscillating force. Because this X-ray electric field is not a constant electric field. It's time-varying electric field, which is oscillating in time. So such an electric field oscillates electrons in the atom. As I already told you, we are not taking very high energy so that it goes and interacts with the nucleus. No, we are not consuming that energy. Our energies are such that X-ray interacts with only electrons of the atom, not with the nucleus. Okay. So when all the electrons in the atom, they start vibrating with the same frequency as the X-ray. So when the electron vibrates, what will happen? Basically, it's accelerated. So it's a charge acceleration. When this charge is accelerated, you know that accelerated charge radiates energy or radiates electromagnetic waves. So what these electrons do, they vibrate. Now let's say that X-ray is only going in one direction initially and falls on the atom. But now atom has different electrons, not only one. You take elements of Z maybe about 10 or something. It can happen for anything. The electrons are oscillating. So these electrons radiate electromagnetic waves in all directions, spherically. So let's look at the diagram. Suppose let's say that I have this incident X-ray coming from one direction, from the left side, and I have the atom here. X-ray falls on the atom. Okay. So when it happens, because usually you see nobody can do experiment with single atom. That's not possible. But just to understand that. So when it falls on the atom, electrons are vibrating with the same frequency as the electromagnetic wave, 10 to the power 16 to 19, whatever frequency you are using. Let's say 10 to the power 17 you are using. The electrons are vibrating at that frequency. The vibrating charge or accelerating charge radiates energy at the same frequency again. They just received energy and giving it back. This is called elastic scattering. There is no loss of energy actually here. We are only talking about elastic scattering. The X-ray comes in and it interacts with the lattice, atom, and only what is the difference? In incident wave is coming only in one direction, but outgoing wave is going in all directions. It's a scattered event. The atom scatters X-rays in all directions. This is for single atoms like this. Now these X-rays are moving away. But if you have many atoms, like crystal, infinitely many atoms, so there is like periodic arrangement of atoms. If each atom receives such an X-ray, because X-ray is not a single ray you are using X-ray beam, which goes and irradiates a particular portion of the crystal atom. In that portion, we have millions of atoms, millions and trillions of atoms. So all these atoms receive the X-ray, and each one is radiating again. When they radiate, each one is radiating. So these electromagnetic wave or X-ray is going in all directions from different sources. What is the source now? Each atom is a source. Forget about the incident X-ray. Each atom is acting like a source, and they are sending spherically symmetric waves in all directions. Okay. And these waves are going out, and what will happen? These one atom is giving the X-ray, other atom is also giving spherical wave sector. Both can interfere. When they interfere constructively, you get more intensity of the X-ray. And they interfere destructively, you get no intensity. But this is not only for two atoms, you can have, I don't know whether you have studied already, you can have multiple slits, multiple slit interference or diffraction we have studied already. For all atoms, waves are going in certain direction, depending on the crystal structure, in certain direction, they give rise to huge intensity. In some direction, no intensity at all. So where there is no intensity, X-rays are superposed, destructive interference is taking place. Wherever in certain directions, constructive interference takes place, in that direction you see huge intensity of the X-ray. This is what we observe X-ray patterns actually. XRD if you take, actually what we are doing is that only. You cannot get intensity, it's not, if you take a single atom for example, you may observe a uniform distribution in all directions. In all the directions, you have the same intensity of the X-ray. But when you have periodic arrangement of atoms, you don't have same intensity in all directions. In certain directions, very high intensity. Then in some direction, no intensity. Again, some intensity. Like that it comes actually. So that's what we call it X-ray intensity. Basically, X-rays are scattered by atoms. The scattered beams interfere and produce diffraction patterns. Okay, so basic experiment, if you see, it looks like this. You have an X-ray coming in and you put a crystal there. Okay, and X-ray passes through the crystal, and on the other side you put a photographic plate. So what will happen? You will always have zeroth order. You know about grating diffraction you have studied already, right? Grating. When you put a grating in front of the light, from the other side you are observing. You see a central maximum. That's what we see, direct beam. There is no diffraction. It has gone in the same direction and produced a print on the photographic plate. That is the direct beam. Exactly same thing what you observe in grating. And then you go up the first order, that is refracted. Go down, there is a first order. Similarly, second order, third order, you can have, depending on the grating, you can observe up to third order, fourth order maybe. Okay. So because what is your grating? Grating has slits actually, right? Parallel slits are made on the grating. Maybe there are huge number, maybe per inch. You have 50,000 sometimes lines actually, 50,000 slits in one grating. If you have that kind of grating, you observe a zeroth order maximum directly, and then first order, second order, like that works. But here is also working similar to grating. That's very, very similar. And the thing is, there you have a two-dimensional grating, a plane, but crystal may be a three-dimensional grating because you have atoms in all XYZ directions. There is no one plane, particular plane. Okay, but things are very, very similar. What you do in grating diffraction is very similar. Only thing is there the light beam is, the ordinary light is used because your slit size is of the order of visible light. But here we need to use X-ray because our slit size here is of the order of X-ray wavelength. That is the only difference. It is very similar to grating actually. Okay. So yeah. So crystal behaves like a grating. But what is the formula for grating? Grating equation actually. You know that A sin theta is and lambda for constructive interference. Now the problem is, will the similar equation work for crystals also? That is question. I'm not saying that this works for crystals, but there must be similar equation for crystals as well, right? So we have to see that whether what kind of equations will work. That some of you know already, but it is behaves like simple grating. Okay, just to show that what exactly happens when you have infinitely many atoms. I don't know what has happened to my X-ray that has been covered by the image maybe. Don't worry. So I have the incident beam coming from the bottom. Okay, here this parallel line I have shown that the incident wave is going like this, and these dots are actually atoms in the crystal. Now all of them receive this X-ray, absorb X-ray, and electrons vibrate and radiate waves in different directions. Spherical distribution of waves. But when they go in the forward direction, all the waves are traveling, and if you do it in the same direction as the incident beam, you get interference That's constructive interference. That's a zeroth order we call it. I told you just now. Direct beam, that's called zeroth order. And if you go to the sides, either left or right, you get first order and second order like that will happen. Okay. So this is just actually pictorially showing what happens because this diffraction is occurring because of periodic arrangement of atoms. For example, instead of crystal, you take something like water, liquid, which doesn't have a structure. You will not observe that maxima actually. Or you use a amorphous material, you will not produce that maxima. That first order, second order maxima are related to the periodic arrangement of the atoms. These things are mixed actually. Okay, so this so first to explain this X-ray diffraction. So Bragg has explained it in very simple terms actually. Very simple terms with extremely simple manner. He could explain this diffraction phenomenon. So whatever the equation he gives, that actually tells you in which direction you can get the maximum. So that his equation is very simple because we have actually two people here, WH Bragg. These are father and son actually. Both of them worked on this X-ray diffraction and they explained it by Christopher in 1930 and they shared a Nobel Prize actually. Because somehow it's overlapping that Bragg law I have written that should have been above. Is it happening for all cases? No. Yeah, that's it. So both father and son, they worked on X-ray diffraction, different crystals, and they explained how X-ray diffraction actually works. See, this is a model. Yes, even a model kind of thing, which explains all the X-ray diffraction phenomena. They're very simple model. Okay, so it was done in 1913, and they shared a Nobel Prize. And what are these considerations he has done? So what he says, when you have a crystal, you have atomic planes, right? When you have planes, one atomic plane, another one parallel to each other like that, with a separation d, let's say. So he takes one set of such planes. Now what, according to him, each crystal plane of atoms is taken as partly reflecting mirror. That means when X-ray falls on that, some part of it is reflected and gone. Then it's going inside. Again reflected by the next second one. Third one reflects. Like that it keeps on going. Okay. So that means each lattice crystal plane is taken as partly reflecting mirror actually. Just he does not bother about where are the atoms present, he doesn't care. He says that is a partly reflecting mirror, not completely. Completely reflecting means you will have only one mirror, second mirror there is no light. Partly reflecting mirror. And at each mirror, specular reflection occurs. Specular reflection means incident angle is same as reflection, angle of reflection, right? That's called specular reflection. So each plane reflects specularly. That's what assumption, not assumptions, is the propagations he made actually. It looks like it works very well actually. But when you assume that crystal plane is like a reflecting mirror, that means you are assuming it as a continuous mirror, right? Mirror means continuous. He has assumed it like that. Okay. So, but let's see how it actually works. And each plane reflects only a tiny fraction of X-ray intensity. How much it reflects? That's the question. When X-ray is falling, let's say intensity is 100. How much is reflected by one plane? He says that 10 to the power of -5 to 10 to the power of -3 of the incident X-ray. That means 100 into 10 to the power of -5. See, it's a very small fraction actually. Okay. Or 10 to the power of depends actually. Where depending on what kind of elements you have in the lattice, in the crystal, and depending on that, sometimes more is reflected or sometimes less is reflected actually. But it always varies from 10 to the power of -5 to 10 to the power of -3 of the radiation incident on the plane actually. That much part is only reflected. If you assume that his incident intensity is 100, multiply 100 into 10 to the power of -5. That part is reflected. Rest is going in actually. Okay. So that means maybe reflection is only 0.0001 something. The rest is going inside, again getting reflected. At each plane, this much amount is reflected. That means about 10 to the power of 3 to 10 to the power of 5 planes contribute to Bragg diffraction. Before it completely intensity becomes 0, X-ray travels by 10 to the power of 3 to 10 to the power of 5 planes. It's a huge number of 10 to the power of 3 to 1000 planes. If it is very high jet element, cannot penetrate much. So maybe 1000 planes it stops. But if it's a light element, It can go further actually, transfer of light rays. Okay, so it depends on X-ray energy and also jet actually. But don't worry, these are some average numbers we have given. That means each one ray to get completely reflected, it interacts with at least 10 to the power 3 planes, or sometimes maybe up to 10 to the power 5 planes. So slowly one by one it gets reflected. So one first ray is reflected by the first plane, then it goes second one is reflected. When these two or all the rays which are reflected interfere constructively in that particular direction, you get maximum X-ray. In some other direction if you calculate, they may interfere destructively. There is no intensity. So like that it will happen. Okay, this is actually, see, you have the lattice planes are like this, crystal planes. These are basically atoms. Okay, this is another crystal plane. They are separated by distance d, let's say interplanar spacing. Okay, so when the X-ray is falling on such a thing, what is the assumption? We takes each plane as a partly reflecting mirror. Now that's why I removed these atoms actually now. Why? How does it matter for us? That's why some people are worried actually when we derive Bragg law. If we ask them to derive, they put one point here. They put one point. That's not necessary because he has assumed that it is a partly reflecting mirror for you. No atoms, nothing. He has replaced that plane with partly reflecting mirror. That you see when the first ray is coming like this and getting reflected. And it will also go inside actually. It will go inside, but we have taken two beams separately, 1 and 2, and to calculate the path reference we are doing. But this ray, the first one, will go inside and get reflected again. That will go further, get reflected. Similarly, this also. This will have a reflection here also, but for convenience, we avoid that actually. This second one will have a reflection here, but that's not important for us to derive this Bragg law. Then it goes down, then again, it has gone from the second layer, but third it can go. Both will travel like that. This multiple scattering takes, multiple reflection takes place for one ray actually. So single ray is not having a single reflection. So, but to derive the Bragg law, those are not important actually. So what we need to do, just take one ray which gets reflected from the top surface, and another one you take which gets reflected from the bottom surface. Okay. So what is the path difference between these two? Because depending on the path difference, you get either maximum or minimum, right? So this how these waves, when the waves are superposing, you get maximum minimum. You have a condition actually. If path difference is equal to integral times wavelength, you have constructive interference. The path difference is equal to n plus half lambda. Then you have destructive interference. But we are interested in where are the maximum condition. So that should be path difference should be n times lambda, integral multiple of lambda. But how do you get that? It's very easy. You must have derived. Suppose you take the first ray. First ray is going like this. Second ray is going down and coming up. If you want to find the path difference between these two, which is traveling the more path, more distance, ray 2 is traveling more distance compared to ray 1, right? How much extra path it is traveling? You can just find out by drop a perpendicular from this point to the second ray at A. That's a perpendicular. Drop another perpendicular from this point to ray 2 on the reflected ray. One of the incident ray side, another on the reflected side. Now if you see A, B, C, that is the extra path traveled by the ray 2 compared to ray 1. We remove this path, both ray 1 and ray 2 have the same distance actually, travel same distance, because up to here they are coming parallel, right? Up to this one they are coming parallel. From here they are going parallel again. So only extra distance traveled by the ray 2 is AB plus BC. We can find AB plus BC and equate it to n times lambda. We can get Bragg law actually. Okay. Okay. So that is very simple, because if you want to calculate this, usually in this X-ray diffraction, we don't take the incident angle from the normal actually. We always take the angle from the surface of the crystal, not from the normal actually. Okay. So it's usually taken as grazing angle. Theta is measured with respect to this. That's why I told you that X-ray gets specularly reflected, right? you should get specular reflection of the X-ray. When you have specular reflection of the X-ray, see, if it is theta here, that will be theta on the other side also. But theta and theta we are writing because of specular reflection. It is like a mirror actually. So and then angle between these two also becomes theta here, because these are perpendicular to, one is perpendicular to this line, other one is perpendicular to the ray. That is also theta, that you can verify geometrically. And then if you find AB, you want to find AB, that will be just d sine theta. This is d, right? It's like distance is d, that will be d sine theta. Similarly, BC is also d sine theta. So AB plus BC is 2d sine theta. If that path reference is equal to integral multiple of lambda, then we have constructive interference. Because when you do an experiment, you want to see where is the X-ray. You cannot see where there is no X-ray. There is no X-ray coming, what is there to do, right? So you want to see where the X-ray is coming, you put the detector in that particular direction, try to get some intensity. That's why you always go for the maximum condition. 2d sine theta is and lambda. But you know that d is the interplanar spacing, right? D is the interplanar spacing. That depends on the Miller indices of the plane. D is not just, you cannot write DHKL. I have written it here, I have changed its slide notation. DHKL. That means D depends on Miller indices of the plane. Not only D, then theta also depends on the Miller indices of the plane. If you change for a different plane, if you do the experiment, you get different theta actually. Theta also depends on HKL. So you can write Bragg law in more informative manner, that 2D HKL sine theta HKL is equal to m lambda. Okay. So when you write that, so this equation you see, it looks very similar to what we have in grating equation, right? It looks very similar, except that there you have a sine theta, from here 2d sine theta. It is very similar. So it is, that is the reason I said this is very similar to grating. Okay. But only difference here is because to derive, Bragg has assumed a very simple model. This model is very simple, you see. If you take it as a mirror with specular reflection, and he is deriving this law. But this law is spectacular that it explains all the X-ray diffraction. You can find out all the angles where it goes. If you know the crystal structure, crystal is given to you, wavelength is given to you, okay, and the crystal is given, DHKL is known, lambda is known. Take n is equal to 1, for example. You will be able to find in which direction the reflection is coming, X-ray is coming. It's miraculous actually, because these assumptions are very simple. That's why they got the Nobel Prize. And not only just by deriving this law, but they have explained crystal structure of sodium chloride, cesium chloride, those layers itself. What is the actual structure, they will explain. So this is one simple equation, but you must remember that most important thing, what are his considerations? How did he arrive at this law? Because he assumed that each crystal plane acts like a partly reflecting mirror. And how much it reflects? Of the order of 10 to the power minus 5 to 10 to the power minus 3 maximum. Okay. That means some small fraction is reflected every part. That means overall around 10 to the power 3 to 10 to the power 5 planes are involved to completely remove an X-ray. So from that assumption, he has derived this 2d sine theta is and lambda. So he has assumed that there is a specular reflection at each crystal plane. And here another important thing is, it is elastic scattering of the X-ray. Because initially I told you actually, when X-ray is incident, because incident on the crystal means what? It is basically incident on the atoms. Atoms irradiate at the same energy, same frequency. There is no change in frequency. There are things about inelastic scattering, but those effects are very minute. But this is actually elastically scattered. It's exactly similar to, suppose if you throw a ball at an angle, it goes and hits and goes in some other direction without losing its energy. There is no loss of energy. Elastic scattering, exactly same thing actually. Atoms also. But microscopically, it's not so simple like just throwing a ball and getting it. Microscopically, because X-ray is absorbed by an atom, electrons oscillate and they irradiate. But such things are not happening here. For a ball case, it is different. We assume that ball is continuous, ball is going, hitting and coming back, and there is no energy loss actually. That's also elastic scattering. It's also similar, except for oscillation of electrons and re-radiating. It's also similar. Okay. Now, that is about Bragg's explanation of X-ray diffraction. Actually, that's the way how Bragg has explained. But there are other people who work. So Bragg's explanation is actually, you see, he has considered these lattice planes and they have been replaced with mirror. Okay. So that is all done in direct Breve lattice because we have assumed that there is a despacing and it's direct lattice is a Breve lattice. But there is somebody called Tom Lave for formulation of X-ray diffraction by crystal. He actually works in reciprocal lattice. He does not assume even these lattice planes or anything. He's actually, this is more general. His approach is more general, but explains the same thing again, not very different. You get maybe the equations become vector equations, but otherwise not very different. That way, Bragg law is a scalar equation, which is very simple. But all the way conditions are vector equations. But this is also very simple. But he starts with a very general. He also got a Nobel Prize. Lave also has a Nobel Prize. But he explains it from a different perspective, without considering specular reflection or anything. He just takes it as a atoms are sitting at the Breve lattice positions. Okay, that's what he considers. So Lave considers the crystal as composed of identical microscopic objects. At each lattice point I told you, you can have a basis actually. That basis may be a composition of atoms, not single atom also. He takes it that way. So at Breve lattice point, you have the basis. Placed at the sides are of a Breve lattice. Each point re-radiates X-ray in all directions. Same thing. Each point re-radiates with point means that may correspond to group of atoms. That is basis actually. That is radiating in all directions. Okay. Then no specular reflection assumed because there is no mirror. There is no mirror. Where is the specular reflection? Okay. He does not start with the specular reflection of taking in terms of crystal planes. He talks about each point on the Breve lattice scatters X-ray. So let's look at this. Suppose when you have the way formulation is like this. Suppose I have taken two black dots, one here and other one here. These are the, assume that these are the two lattice points for you. Okay, separated by a distance d. That may become Breve lattice vector later. Okay, that I have written it as bold letter d. That's a vector actually. Now let's imagine that you have incident wave vector k of the X-ray. It's coming in some direction. It's practically when you want to do an experiment, what you do, you have to pass X-ray in some direction, right? So that's incident direction is coming like this. It is taken like this. The beam is coming like this and falling on both the lattice points simultaneously. Okay. Now, once it falls on this lattice, it gets scattered in all directions. But see, it gets scattered spherically in all directions. You cannot look at simultaneously in all directions. You must put your detector at some position, gradually rotate and go to the other position. So let's say that I'm looking in this direction. X-ray scattered. What is X-ray? Scattered in escape time direction, which is like this. You can also look at in some other direction. That's not issue. So I just keep my detector in this side, let's say. I want to look at in this direction what is the X-ray coming. What kind of is it like constructive interference or destructive interference? That's what I want to look at. Now what has happened? This separation is d and this angle of incidence, let's call this theta. Okay, and this is theta prime. They are not same, not like earlier. So they can be different. Now again, I want to find the path difference between the two rays. One ray has gone from here, other one has traveled to the second atom. So if you want to find the path difference, extra path traveled by ray 2, you have to calculate, you have to drop a perpendicular from first point to ray, the incident ray, that is dotted line I have showed actually. I'm not able to get this cursor somewhere. Yeah, this is one perpendicular, other perpendicular is here. Now the total path, extra path is this one. This much you have to calculate. If you calculate, like as I thought that people are not much interested in doing math, so I removed all those things. D cos theta will be this one, this line, and this side will be d cos theta prime. So the total path difference is d cos theta plus d cos theta prime. Okay. Now, but I want to write it in a little bit of vector form for convenience. So d cos theta can be written as d dot k cap, d vector dot k cap. K cap is the unit vector in that direction. That will become d magnitude of d into magnitude of k cap, that is 1. That is d cos theta. Similarly, if you write for this, you cannot write it as d dot k cap prime, but you should write it minus d dot k cap prime, because the angle has a problem here. You see, this when you measure the angle between any two vectors, you must take it like this. Suppose here you see first angle theta. This ray is coming to this point. D is also pointed towards that point. That angle is okay. But here it is different. Here it is coming and ray is going. Angle should not be defined that way. That theta prime is not properly defined. Theta prime actually should have been defined line like this and this angle. Okay. So because of that, when you put it in vector form, it will become minus d dot k cap x, k cap prime. This will become minus d dot k cap prime. So this is what you will see actually. Path reference is d cos theta plus d cos theta prime. That is d dot k prime instead of k prime I have written n cap x, n cap minus n cap prime, where n cap is a unit vector along k incident direction. N cap prime is the unit vector along k prime direction. Instead I was studying k and k prime, but it's put in n cap x. Okay. So anyhow, this little math we cannot avoid. Okay, we have to d dot n cap minus n cap prime. That is the path reference. If it is equal to m lambda, let us not write n lambda because then we are using already for Bragg law. Okay. So and also maybe some other place we'll get that again. That's why not to confuse. Let us put it as m lambda. Here is m is an integer. Okay. D dot n cap minus n cap prime is equal to m lambda. If you multiply the whole equation with k is the magnitude of the wave vector. Okay. So if you multiply with k, d dot k into n cap minus n cap prime, m k lambda. What is k in terms of lambda? 2 pi by lambda. Right? K in terms of lambda is 2 pi by lambda. Then this we can cancel out this lambda here on the right side. D dot n cap into k is k vector, n cap prime into k is k prime vector. K minus k prime. What is k and k prime? K is the incident wave vector. K prime is the outgoing wave vector. As I already told you, this is we are considering elastic scattering. That means there is no change in energy. That means no change in k actually, magnitude of k. K vector direction changes, but magnitude doesn't change. That means magnitude of k is same as magnitude of k prime. That's the elastic conditioning. Okay. But k minus k prime cannot be net zero. These are vector reference. It's put 2 pi m. Suppose if I take for crystal the lattice, replace d with r actually. D is the vector connecting 2 points, right? That is nothing but lattice vector actually. Okay. So if I put d is equal to r, then r dot k minus k prime is equal to 2 pi m. Okay. If you want to write it in the exponential form, suppose when you have 2 pi m, e power I into 2 pi m is 1, right? E power minus I into 2 pi m also 1. Is it not right? E power I into 2 pi m is 1. E power minus I into 2 pi m also 1 actually. Okay. Yeah. So this I have put it actually like that here. E power minus k. See, I will not put k minus k prime, but I made it k prime minus k because r dot k minus k prime is 2 pi m. That's an integer. Integer times 2 pi. R dot k prime minus k is also minus 2 pi m. But both will give you 1. So I have changed that thing here. K prime minus k dot r e power I. Okay, is equal to 1 because whether it is my e power I pi or e power I into 2 pi or e power minus I into 2 pi, both are same, both are 1. That's why I can change this k prime minus k. That's for some purpose. What is k prime minus k now? Because if you look at your reciprocal lattice definition, e power I into g dot r is 1, right? R is Bragg lattice. E power I into g dot r is 1, but same result we are getting here. In that case, k prime minus k must be equal to a reciprocal lattice vector. K prime minus k must be equal to a reciprocal lattice vector. Otherwise, that equation is not satisfied. So that's how you see this called the wave condition. K prime minus k is equal to reciprocal lattice vector. We works in this result comes in reciprocal lattice because these are wave vectors, wave vector difference. Change in wave vector k prime minus k should be equal to the wave condition. I will show you geometrically what this means actually. So that means constructive interference will occur when only when the change in X-ray wave vector equals reciprocal action. But this result is same as drag condition. You can get drag condition from this, not other way. See, once you have a vector equation, you can always derive a scalar equation by taking the magnitudes. But other way is not easy. But this is more general. You can go back to this drag law from this. Okay, what we have seen is actually like this. Let's say this is the crystal I have, that blue rectangle, and incident X-ray, K. I have put it in here, see. Incident X-ray, I have extended it down a little bit. It's coming down, and scattered X-ray is here. So that's K prime. This is K and K prime. K prime minus K. That should be G. That means just connect K to K prime. That difference is G. That what is the angle between K and K prime? If you see that angles theta, what we have defined there, angle between K and D. Okay, that is theta. But angle between K and K prime will be 2 theta. If this is taken as theta, for example, raising angle theta, this will become 2 theta. Okay. So this is overall change because K wave, incident wave vector rotates by 2 theta to get scattered wave vector. This line connecting this K tip of K to K prime is actually G. That is reciprocal. I already told you, reciprocal Lex vector must be perpendicular to the planes. There are planes here along this horizontal direction, the crystal. So it must be perpendicular to the planes. That is obvious. That's what we are getting at. So when K prime minus K is equal to G, you get constructive interference. Okay, that's called level conditioning. But how to get drag law from this? Let us look at the same diagram. It's slightly plotted in a different manner. Suppose I have incident wave vector K at an angle theta with the surface, and it goes away at an angle same theta it goes. Okay, because if you just take this as theta, this will also become theta. You can verify that. K prime. Now, our reciprocal X vector is perpendicular to the plane, actually, like HKR plane. It is perpendicular to the crystal plane. It is like this. Now, this is K prime. If you do, this is K direction is like this. If you do minus K from here, you go like this, right? You just transfer it there and make it minus K. You go like this, but their path are the opposite antipath. Now, K prime minus K is equal to G. Same thing, same equation we are satisfied actually. But apart from that, this figure will also give you one more thing actually. What is that extra we get? Okay. Yeah. So if you see this, if you take the component of K along G, okay, component of K along G, it will be K sin theta, right? K cos theta will be along this, K sin theta will be along the direction of G. That is K sin theta. What about the component of that? Component of this minus K. If you take the magnitude of that component of the magnitude of the component, this will also give you K sin theta. We say minus K sin theta, but if you take the magnitude of the component, I want to just measure the total component along G. K sin theta is this much. Another K sin theta from here. That means G is equal to 2K sin theta. G is equal to 2K sin theta because we are not writing vector. That's why I said it's minus or plus, it doesn't matter. You take this length is K. What is the projection here? Because this is also theta. What will be our theta? If this is theta, then this will be 90 minus theta, right? Yeah, this will be 90 minus theta, right? So this will be K sin theta. Projection of these along G vector is K sin theta. Just take the length only. Don't worry about direction because both K and K. So this is K sin theta, that is half. Another K sin theta, that is about total 2K sin theta. It is G. Or also this figure also tells you one more thing. Projection of K along the reciprocal X vector is just half G equal to half of the magnitude of G. That's what I put this dotted line here. You see, this dotted line says K sin theta is simply G by 2. Don't write vector. K sin theta is G by 2 or 2K sin theta is G. Then what is G? K is nothing but 4 pi by lambda. G is equal to 4 pi by lambda sin theta. If you know theta and lambda, you can calculate the reciprocal X vector. But what is G actually in terms of D? You know the 2 pi n by D. That's the reason I told you not to put same m there actually. 2 pi n by D. That is the perpendicular to the plane with the interplanar spacing D. That's the reciprocal X vector magnitude. 2 pi n by D equate it. 2 pi n by D is equal to 4 pi by lambda sin theta. You get 2 sin theta and lambda. So from this you can get back to our this thing. And with this point I have written here, projection of K along G is G by 2. It's a very important consequence actually. So a lot more things can be discussed about this level condition and some implications, but that is not important. So this much little math we cannot avoid in any case. Okay. Yeah. Now, yeah. Before going to that, I will discuss at the end about some special crystal structures. Only diagram I am showing. Any figure is shown. No, don't worry. We are not going to say any mathematics again there. So with this level diffraction condition, you can again get back to the Bragg condition because level condition is in vector form. Going back to scalar form is always possible. But starting from Bragg condition, you cannot get back to this. Scalar equation from the scalar equation. It's very impossible problem to get a vector equation. Okay. You have unless you have other information separated. Okay. Now when this diffraction thing, when I remember this Bragg law, that actually when we were in MSc, we used to have some viva. Whenever we have to do experiment in the lab, we have this X-ray diffraction experiment was there in MSc. Central University, Hyderabad. So when we on the photographic plate actually, not like now we don't have the software in this thing. So when we used to have a professor actually. The fact his name is Professor Srivastava. He looks like a big hair and a big scientist. And he also is like that, somewhat how sometimes he doesn't live in the world. He's thinking something, suddenly he's walking and stops somewhere for maybe some few hours. So he used to behave like that. So he called me for Viva. Because people are going one by one. He asked me to derive Bragg law. Bragg law means it's very simple, so I just drop 2 lines and derive Bragg law. Then he told me, tell me what is intensity. Because intensity is not given by Bragg law or level condition. What is the intensity? No one knows. They are not saying. In which direction X-ray is diffractable. Intensity is not given by this thing. But I didn't know that time. I was thinking that maybe something I have to do with the Bragg law. Whatever you do with the Bragg law or level condition, intensity will not come in. Okay. But the professor is very, he told that time he explained some structure factor thing, but I don't remember. But he's a very senior person and a lot of knowledge actually. And people used to call it Einstein those days. People that because he's always thinking and sometimes he's stopping in between. And he forgets also. Today he may talk to you and tomorrow he may not remember. So once what happened, he took his wife for shopping. It seems, I didn't witness that, but it seems it happened someday before we joined for MSc. So he went for shopping. They went in car was parked somewhere, and both were shopping. And in between, his wife was busy in maybe buying something. That time he came out. And he took his car and came back home. That time he has forgotten that his wife is there. And he came back home, then she didn't find such everywhere, and finally she went and searched in the parking area, no car. But she has understood that this fellow has gone. But she knows little bit about him because sometimes he was forgetting things. Then she has to call the department and get somebody's help to go. But that was okay. So he used to do like that. By learning physics, sometimes people become little mad actually. They forget things. That time people used to say whoever research scholars are there, some research scholars, they used to do joking, or maybe some people really want it. They used to say that I will also become very great. I will get married and leave my wife in the market. Then I will become great. But if somebody does it now, they will go to police station. But those days it was okay, not such serious actually. Okay. So that's what I remember when this Bragg law is seen actually. Okay. Now just I want to tell you about sodium chloride structure. It's a very nice picture. Okay. I made it actually. Okay. It's not downloaded from anywhere. You can also make it if you like. It's very easy. So because when this Bragg and his son, they worked actually on this sodium chloride structure initial days. They only told that sodium chloride, earlier people used to believe that sodium chloride has sodium and chlorine interacting with each other. It's like a molecule. These molecules are there in the crystal. But these people don't know no molecule. There are atoms arranged in a crystal, but no molecule. And its structure you see. If you want to understand the structure, first look at sodium. Forget about chlorine. If you only look at that thick blue dots, you see a face-centered cubic lattice, right? You can also see all the corners are occupied, okay, and face centers are occupied. So sodium has a face-centered cubic lattice. Similarly, actually, it doesn't look like here for you, but if you start from here, in middle plane, and extend it to this side, even chlorine also will have face-centered cubic lattice. Such structures are called interpenetrating face-centered cubic lattices. That means sodium first forms a face-centered cubic. Chlorine also forms a face-centered cubic. They are interpenetrating. So, if you ask what kind of lattice sodium chloride has, you should say face-centered cubic for each, both of them. One for sodium, one for chlorine. They are interpenetrating. And if you want to know what is the lattice parameter of sodium chloride, lattice parameter means sodium to sodium distance, not sodium to chlorine. If you take Na to Cl distance, that's called bond length. This is bond length. But chlorine to chlorine or sodium to sodium, that is called lattice parameter. So how to make this thing is very easy. First you put all sodium atoms in the what is the face centered and corner atoms. Then what you have to do, all edge centers. You take edge means this is an edge, this is an edge. Edge centers should be to keep for chlorine atoms. That's how it is generated. But that doesn't mean that chlorine has edge center lattice. No, that's why I said. If you want to know what is the lattice formed by chlorine, you have to start from here. Okay. You see, from this is a face center. You go to the other plane on the right side. You create one more plane. Then you will see that chlorine is also forming a face-centered cubic lattice. It is two interpenetrating face-centered cubic lattices, both sodium and chlorine. So similarly, suppose cesium chloride structure, that is somewhat simpler, not so complicated. So this is one unit cell. Can you tell me how many sodium atoms are present in this unit cell? Can you just find out, try to work out how many sodium atoms are present? Because it's a face-centered cubic, so there must be 4 sodium atoms, right? This face-centered cubic, you know that 4 lattice spots. Okay, that's 4 sodium atoms. If you have 4 sodium atoms, there are 4 chlorine atoms also. So total it is actually 4 sodium chloride molecules are there in this. So when you take sodium chloride as one lattice point, that means this unit cell has 4 lattice points. That's why it's a face-centered. Okay, but because we have 2 different atoms, see, I cannot say that this is one Bravell lattice point, this is another Bravell lattice. No, not like that, because they are dissimilar atoms actually. But overall, if you see, you have 4 NaCl molecules effectively present in this cube, bigger cube. But if you take a smaller cubes, you see there are so many smaller cubes. The smaller cube has 4 chlorine and 4 sodium at the corner side. Okay. If you have 4 sodiums at the corner, what is the effective atom number? 1 by 82, 4. That is equally half. You have half sodium, half chlorine in the smaller cube. In smaller cube, you have half sodium, half chlorine. If you have half sodium, half chlorine, that's not even primitive cell. Primitive cell means you need 1 sodium, 1 chlorine. Then you can say that it's a primitive cell for sodium chloride. So this is half the primitive cell, smaller one. Okay, now these are some details, but if you want to know, understand what is the structure of sodium chloride, and whenever something is asked what kind of structure it has, it is actually face-centered cubic. Two interpenetrating face-centered cubic lattices. Sodium has its own face-centered cubic, chlorine has its own face-centered cubic. And a lot of maths is there here also, but I removed all that because you people are sleeping. Okay, now let us look at cesium chloride structure in a simpler. In cesium chloride, you have cesium sitting at the center, body center, and chlorine at corner position. So what kind of lattice is this? It should not be called as body centered cubic. No, because body centered cubic actually means same type of atom has to be present at the body center also. Then you can call it body centered cubic. Otherwise, not body centered. It is actually simple cubic lattice. This is a simple cubic lattice by chlorine ions. Similarly, if you extend unit cells on either side, on all sides, you will also see that cesium also has simple cubic structure. So it is simple cubic lattice. Whenever this kind of thing is there, don't say it is body centered. Body centered actually same lattice point has to be there, but this is not the same. Chlorine is not same as cesium. You cannot call it body centered. It is actually simple cubic lattice by chlorine. Another simple cubic lattice by cesium. They are interpenetrating simple cubic lattices. This is somewhat simpler than if you look at what is the effective number of cesium here only one. Chlorine has one. Cesium chloride. One molecule is present here. This is one molecule is present in this cell actually. Okay. I think that is fine. We did a lot actually. So then only one thing is left. But tomorrow, it's the last day. We have to find out how to get the X-ray intensity. The diffraction, because when you say Bragg law and it's the diffraction, they only tell you what direction you get the maximum intensity of X-ray. But they don't say how much is the intensity. If you want to understand how much is the intensity coming from the X-ray diffraction in this given direction, you must know what is called structure factor. Okay, structure factor is something to do with the basis. Because how much is scattered by the basis, that is called structure factor. So we look at the structure factor tomorrow, but little math cannot be avoided. Okay, because we cannot keep telling stories all the time. But that we work out little mathematics, and then we also understand that's not very great mathematics. So we'll do that. And, yeah. So if you have any questions, let me know.
Hello, sir.
Yeah.
Sir, I am Shahrukh. So I have a question there.
Yeah.
That you have told about the elastic scattering, where the
Yeah.
energy is completely transferred
Yes.
after the scattering.
Yeah.
So is it necessary that if the scattering is elastic, then is it necessary that the collision should be elastic or not?
Yes, of course. No. Because see, in case of when the X-rays interact with the atom, you don't actually call it collision, means you should consider it as a photon then, right?
Yes, definitely.
Unless you see collision means particle, you can call it collision. But then you are talking X-ray interaction. Yes, it is elastically scattered. Means collision has to be elastic. No? Otherwise, the energy is already lost, right? So X-ray interaction with
But
atom. Yeah, yeah. Tell me.
But sir, I have some issues for Compton scattering, where the
Yeah.
scattering is not elastic because the output, because the scattered wave energy is
Yeah.
lower than the incident photon.
Yes, that's right.
The collision is elastic because when we
Hmm.
started our calculation,
Yeah.
we used to do the energy momentum conservation calculation. So how is it possible that the collision is
No.
the scattering is inelastic, but in our collision is elastic?
But do you really use energy conservation in Compton scattering? Let me.
Yes, I actually.
No. You're wrong. Actually. No, the problem is like this. You are wrong. Problem is when you say there is a Compton scattering, right?
Mhm.
So you always include in that energy term this electron energy also, right? Just
Okay,
check your,
okay, okay.
yeah, that
Yes, sir.
electron is
Yes,
not
yes,
even in your system now, right?
yes,
So
yes.
that's
That is the recoil
energy.
electron. Yes, yes, yes.
Yes, that has to
Yes.
be there. Otherwise, you don't have it.
Okay, okay.
That is not right.
Yes,
So
sir. That
that
actually
is
this is a
inelastic.
doubt.
Yeah, that's
Yes, sir.
okay. It's
Yes,
a
sir.
good doubt, but that collision is inelastic. Yes,
Uh-huh.
in
And
Compton scattering.
okay,
Yeah,
sir. Okay. Thank you, sir.
yeah,
Actually,
but it's a good doubt
this is a
actually.
long
That
term doubt for me because I
okay,
am
but no, that's a reasonable and sensible doubt. I will say. Even
yes,
when you ask, you are the first person to ask me that doubt. I also didn't have that doubt. But anyhow, when you
yes,
think about it, it's good. Always want to think about it. Because don't take things for granted. Okay,
yes,
it's
yes,
nice
yes.
to think for it.
Okay, sir. Okay, sir. Thank you.
Yeah, and I really I forgot to say a little bit when I told actually. So about this Young's double slit experiment and single slit diffraction, all of you must read this Resnick and Hadley. There are Resnick and Hadley plus two level books, but you read it and read the questions in the chapter also. Extremely good book. You must read. There are a lot of books now, but there is university books book, but nothing is comparable to that, I think. Because these books are very, very good. I only studied in my MSc, unfortunately. But even now I do it sometimes. So this interference, the double slit, the Young's double slit, and interference and diffraction. Everything you read in that book once. Before you complete your BSc, at least you read that. Read some chapters from Technical Habit. And again, SURMA is very, very good book. You know, that is too much of school feeding actually. And mostly it tells how to solve problems. That's very good book. But, you must, after going through that, you must also go through its technical habit. It's very, very important. Okay. And yeah, anything else? Yeah, yeah, okay. Okay, thank you very much. Yeah, okay, yeah, yeah. Okay, thank you, thank you. Okay, have lunch and have sleep, or maybe you're already sleeping, I don't know. Yeah, okay then.